Welcome to this talk, Assessing Rainfall-Induced Volcanic Hazard. My name is Jamie Farquharson, and I'm going to be talking about some of the NASA-funded work I've been doing at the University of Miami, along with Lokon Empung. So I want to thank Zeiss, as well as VMSG and the Geological Society for this opportunity. If you want any additional information, preprints, reprints, or a transcript of this talk, please contact me using the details on screen. So to start off with, I would like to show this satellite image. So this image was derived from Sentinel-2 data, processed via Sentinel Hub. And the first thing I ought to point out is the ongoing eruption visible in this image. If we zoom in here, you can quite clearly pick out a lava flow and an eruption plume. So this is the summer 2018 eruption of Sierra Negra in the Galapagos. But what I like about this image, however, are the other features highlighted here. So these are the peaks of 4 other volcanoes, Fernandina, Darwin, Alcedo, and Cerro Azul, just reaching clear of the cloud bank. Now there are clear orographic effects at play between the volcanic summits and the blanket of cloud, which is part of a complex interplay between volcanoes and rainfall more generally. Throughout the rest of this talk, I won't be talking about the effect of volcanoes on rainfall, however, but rather on the effect of rainfall on volcanoes. Now, many rainfall-related hazards, such as mass wasting events, are exacerbated in volcanic environments. Volcanoes often have steep slopes. They can be composed of variably consolidated and easily mobilized deposits, and there may also be large thermal gradients at play. And indeed, there's a clear link between heavy rainfall in volcanic environments and the potential for a range of volcanic hazards, so things like the generation of lahars and other non-eruptive hazards. Now lahars, dome collapses, and things like this can all be thought of as secondary phenomena in that they involve the remobilization or reactivation of previously erupted material. However, what about primary volcanic activity? We define here as discrete eruptions of lava, tephra, and gases. Can rainfall actually trigger or influence primary volcanic activity? So there are several previous examples where researchers have correlated the two phenomena. In the 1950s, a sequence of eruptions at Las Pilas in Nicaragua was attributed to volumetric expansion of rainwater in the vicinity of the magmatic system. More recently, Larry Mastin correlated dome explosions at Mount St. Helens with passing storms. An excellent series of papers by Adrian Matthews, Jenny Barclay, Joshua Tarran, and others have addressed the linkage between rainfall and primary volcanic activity at Soufriere Hills volcano. Sophie Violette and co-authors found a correlation between eruption frequency at Piton de la Fournaise with the seasonal rainfall. A statistical correlation has been found between collapse-induced explosions and rainfall at Gunung Merapi in Indonesia, and a similar relationship was identified at Unzendake in Japan. At Kilauea in the US, a statistical correlation between rainfall and eruption occurrence was found by Fred Klein of the USGS back in the 80s. And this was highlighted more recently in a paper by myself and Falk published last year. So all of these references are provided at the end of this video. So now the question remains, are these geographically discrete examples symptomatic of a broader link between the hydrological cycle and volcanism? So the majority of these studies have relied on sparse and often non-continuous rainfall gauge data. However, with the advent of spaceborne precipitation detection systems, we can now address this question on a near global scale. So the graphic on screen illustrates our orbiting rainfall detection constellation, including the NASA JAXA Global Precipitation Measurement Core Observatory. So with this network of satellites, we can obtain close to global coverage every 3 hours, with a data set that goes back continuously for over 20 years. So here's an example of some retrieved and processed data showing subpolar rainfall from early 2000 through to 2001. And even at this scale, you can pick out individual monsoon systems, individual storm systems that we can look at over time. Now, given a coordinate of interest, we can also extract time series of rainfall. And this is something that we do in order to assess whether the duration of timing of annual rainfall plays a role in modulating eruption frequency at different volcanoes. We first determined localized rainfall patterns for each volcano. So in particular here, we're interested in the so-called rainy season. So note that I use rainy season to refer to the period or periods of the year when a location receives the majority of annual rainfall on average. So we adopt a novel spectral approach in order to do this. First, we extract the rainfall time series of length L years. We then look at this in the frequency domain, and we extract the sum of the first two L components and the sum of the first L over 2 components, the Fourier components, and we define the onset and withdrawal of the rainy season where these intersect. So this is good for a few reasons. Firstly, that it's generally applicable. We can apply this automatically to all volcanoes covered by the GPM satellites. It takes into account both long period and short period effects, and it's not arbitrary. So we're not just setting a threshold of rainfall that wouldn't necessarily be applicable at different places on the globe. So the extracted rainy seasons are shown here with the black markers, and then in order to kind of extrapolate these data beyond the time series that we look at, we can then take the modal value for any day of the year across this time series, shown here in red. And this is plotted now in polar coordinates, so we can think of this like a clock, where 12 o'clock is January 1st, and the days of the year proceed clockwise around the graph. So the red section is where relatively more rain is detected, so what we can call the rainy season. And our approach does pick out the kind of signals we would expect. So at Semeru, we have a very typical 6-month unimodal season. At Awu, we have a bimodal rainy season distribution, which is a function of 2 competing monsoon systems. And at Uluwon, we have a more complex multimodal system. So for any given volcano, we can also plot eruption dates, so obtained here from the Smithsonian's Global Volcanism Program database. So this is an example of Kilauea, and the radial ticks around this polar plot just show the day of year for any given eruption. So we can calculate probability, which we define as the length of the rainy season divided by the length of the year. So in this case, it's almost 0.5. Big N is the total number of all eruptions. Little n is the number of wet eruptions, so the number that occur within the rainy season. And using these values, we can then calculate a theoretical distribution. So the probability that the observed distribution could occur by chance. That looks something like this, as shown. So in this case, the maximum probability is just under 30 rainy season eruptions. So that's what we would expect if this were happening just by chance. In reality, we see a value much higher than this. So 37 eruptions across this time series that occur within the rainy season. And that is more than 2 standard deviations away from the theorized mean value. So we can say that there's a statistical tendency for eruptions at Kilauea to occur during the rainy season. So that just gives us information for one lag or one time series. A lot of the mechanisms that I'm going to talk about later on are associated with a lag or a delay. So we can actually take this into account as well and offset the window across which we're counting up eruptions. So the graph is just showing the relative eruption count, so little n over big N, for any given lag. So the single datum that is shown on screen is the same as that in the previous slide. We can offset our window by, say, 30 days, 60 days, 90 days, and in fact, every possible theoretical lag, and we get a signal that looks something like this. So using these data, we can then calculate the theoretical distribution for each observed n over n value. And again, that gives us kind of a probability as a function of a given lag. And just to highlight that we see the lowest value hovering around 0 lag, so a lag of 0 days. So we go one step further, and we can normalize both of these parameters to within the range 0 and 1. And then we come up with a scale probability function, or a scaled count probability, which is just the difference between these two normalized values. We can calculate confidence intervals based on bootstrap resampling, and any part of the signal that exceeds these confidence intervals we can define as being statistically significant. So if we see a peak, then it indicates that significantly more eruptions occur during one part of the year relative to others. And we define a range from -30 to 60 days of lag, within which if we see a peak within this range, then we define the volcanoes as sensitive to seasonal rainfall. And in fact, we come up with 35 volcanoes that pass this criteria. So the first thing to do is to compare how different parameters compare between this kind of sensitive data set, the smaller data set, and the original catalog that they came from. The idea being that if we were taking a random sampling of the initial catalog, then the normalized parameter distributions would be identical. In fact, when we compare the sensitive volcanoes, so the 35 volcanoes plotted on the map there, with the original catalog, we tend to see an overrepresentation of them in tropical and temperate climates. They tend more often to be shield volcanoes than in the original catalog. They tend to be basaltic in composition, or more often basaltic in composition than we would anticipate. And we also see them overrepresented in intraplate and rift oceanic crust settings. Now, if we look at some of the volcanoes that we flagged here, it's perhaps not surprising that we're seeing these parameters occur together. Places like Fernandina, places like Piton de la Fournaise, and Kilauea. So I've talked a lot about statistics, and now I'm going to talk about some of the mechanisms which can be operative at a range of depths. So from superficial or very shallow processes to slightly deeper or flank processes, and then other processes which occur deep within the edifice. So these have all been proposed for previous eruptions that have been attributed to rainfall in the literature. So near the surface, or especially in dome-forming environments, we have the flashing of meteoric water to steam, thermal contraction, fuel-coolant interactions, and pressure increase within pre-existing fracture planes that kind of promotes instabilities. Looking somewhat deeper, we have lubrication of failure planes that can promote flank movement, compounded by weakening through hydrothermal alteration. And deeper in the edifice, we have seasonal variations in load due to saturation and desaturation of the edifice, exceedance of chamber failure criteria due to changes in regional stresses driven by pore pressure, and also the generation of new fractures within the edifice that can then be opportunistically used by intruding magma. And many of these rely on the concept of effective stresses. And what's great is that we can actually model all of these processes, or tie all of these processes together with a single common mechanism, so infiltration. So as rainfall lands on the surface of the Earth, it can instigate a pressure pulse which propagates downwards through the edifice as a function of time. So we can model this as a variation in pressure and time, which evolves as a function of physical properties of the edifice and the permeant fluid, so permeability, viscosity, porosity, compressibility. And of course, this also evolves with depth. Now, depending on the depth zone that we're interested in, we can see different pore pressure responses. And if pressure increases to a point that promotes failure, then we can then have the kind of generation of various volcanic phenomena. So the instigation of dike propagation, for example. So to demonstrate the feasibility of this mechanism, I'm going to show you some case study examples. So the first one is the volcano Karkar in Papua New Guinea. So that's erupted 3 times since 2012. And there are also 2 unconfirmed eruptions in 2009 and 2010. So these are shown on the lowermost right-hand side panel there as vertical lines. So first we can extract the satellite-derived rainfall data, model pressure propagation as discussed in the previous slides. So all you need to know here is that where we have blue, that's a small change in pore pressure, and where we have red, those are large changes in pore pressure. We can take a slice of these data, in this case at 2.5 kilometers below the surface, which is approximately where we think magma migration is going on in this system. And that looks something like this on the lowermost panel. And so what you can see is that for each of these confirmed and unconfirmed eruptions, the eruption date coincides with a peak in pore pressure at this depth. So another example, this is the case of Lokon Empung in Indonesia. Now this is somewhat different. Here we observe that generally speaking there's not a tendency for the volcano to erupt during the rainy season. However, 3 of the last 9 eruptive phases have independently been attributed to rainfall, which are highlighted in red on the lowest right-hand panel. So extracting the rainfall time series as before, we can model pressure changes in the edifice as before. And this time I'll show the signal from 1.7 kilometers below the surface, which is where the magma chamber is. And note that those eruptions that have been attributed to rainfall coincide with these peaks in pore pressure, whereas those that are not, do not. Now in both modelled examples, Karkar and Lokon Empung, I should highlight that the magnitude of stresses shown on screen are probably minima, but nevertheless they're on the order of about 1 kilopascal, which is in line with other theorized trigger stresses. So we also repeat our analyses restricted only to larger eruptions, so explosivities of 3 and greater, to see if we see any potential evidence of larger triggered eruptions. And we do see a few. One such example is Vesuvius. Now, historical eruptions of Vesuvius are typically large, VEI 3 and greater, and have occurred predominantly between July and December. In fact, at least 8 out of 29 have occurred in December. This is a distribution that's statistically non-uniform, as well as being correlated with the wettest times of the year. And there's actually evidence, so textural and geochemical evidence, as well as contemporary reports from the eruptions for the role of external water in at least 6 eruptions. So, for example, contemporary reports of the December 1631 eruption highlighted months of precursory landslides, an immense emission of water, and stated that heavy rains characterized the sign and post-eruptive periods. There was also textual evidence that vesiculation of the magma was inhibited by external water. So in this case, we don't think that the eruptions were, strictly speaking, triggered by rainfall, but rather that precipitation is hastening an eruption that is already building. So making the conditions for subsurface rupture and failure easier because the pore pressure is higher. Now, the surest examples of rainfall-modulated volcanoes are those where eruptions are non-uniformly distributed throughout the year, correlate well with the wettest parts of the year, and are characterized by relatively short seasonal lag times, such as Mount St. Helens, as shown on screen, and Vesuvius, as shown in the previous slide. And we propose that the response of these two volcanoes to rainfall represent kind of end members of a spectrum of eruptive behaviors driven by infiltration-induced stress change within the edifice. So this includes a spectrum of superficial or shallow eruption sources to much deeper sources within the edifice, lag times on order of hours to days compared to maybe weeks to months, repose times that are similarly variable, and explosions that range from small, perhaps violently explosive steam eruptions to much larger magmatic eruptions as well. Now these, or in the past, geographically discrete case studies have indicated a link between rainfall and primary volcanic activity at different volcanoes, even so far as that volcanic events have been attributed to discrete storm systems, such as that shown on screen. And our statistical approach highlights that this may be a fairly widespread phenomenon. So notably, several volcanoes for which a link between rainfall and eruptive activity has previously been flagged are flagged by our analysis, as well as a couple of dozen more systems. Altogether, considering our starting catalogue of around 230 volcanoes, we suggest that around 15%, or as many as 1 in 7 subpolar subaerial volcanoes, may be modulated by rainfall. At this point, I'd like to highlight one of the conclusions of Barclay et al., which is as relevant now as it was in 2006. Specifically, they suggested that meteorological information can be exploited more fully to enhance volcano monitoring programs. And further to this, they highlight that knowledge of regional weather systems and their variability could prove particularly useful in forecasting wet seasons or periods of extreme rainfall with the potential to facilitate hazardous volcanic phenomena. And in the same vein, we argue for the integration of rainfall monitoring into probabilistic hazard analysis of volcanic activity. So we anticipate that satellite-derived precipitation data, now operationally available in near real time over most of the globe, at better than daily resolution, will prove invaluable in integrating rainfall into future quantitative studies, monitoring programs, and probabilistic hazard assessment, especially in remote or otherwise poorly instrumented volcanic settings. So in our 2020 paper, we suggested that as ongoing climate change is projected to result in increasingly extreme rainfall patterns over the coming century, the potential for rainfall-triggered volcanic activity may be set to increase in the future. For the last few moments, I'm going to briefly touch on some of the research we've done on this front. So to understand how and where rainfall, in particular extreme rainfall, may change in the future, we turn to the outputs of general circulation models. So these are used to project temperature and rainfall variability, amongst other things, under different global warming scenarios. And something we find is that models tend not to agree on the absolute value of rainfall variability over time. But where they do agree is on the sign of relative change. So whether or not we will see more or less extreme rainfall with every degree of global warming. So I'm showing here process data from 9 of these models with a parameter I'm referring to as the forced model response. So essentially we take the projected time series of global temperature for each model, the projected increase in extreme rainfall for each pixel of each model, and by comparing the two we end up with a value that tells us the percentage change in extreme rainfall for every degree of global warming. So not all models are the same, so from now on we'll look at where they agree on the sign of change. So first I've highlighted the areas where these models agree that extreme rainfall will decrease. In grey are those areas where there was not sufficient agreement between models to draw a sturdy conclusion. And in blue are those areas where models agree that there will be an increase in extreme rainfall. So of course this is the vast majority. The majority of the planet will experience an increase in extreme precipitation over the coming century. And based on the geolocations of our subaerial volcanoes, we can then determine how many volcanoes are in regions where we will see an increased or decreased incidence of extreme rainfall. So these are shown here, firstly for where we'll see volcanoes that will experience a decrease in extreme rainfall, about 9% of the catalogue. These are the volcanoes where there isn't sufficient information to say one way or the other. That's about a third of the catalogue. And for almost 60% of subaerial volcanoes, we can confidently say that there will be an increase in extreme rainfall over the next 80 years, and this number could be much higher. So given the correlations outlined in this talk, and the well-known propensity for the generation of lahars, instigating a flank movement, and other hazardous phenomena as a result of heavy rainfall in volcanic environments, the case for actively monitoring rainfall in these settings is clear. So to sum up with some key takeaways, we've been looking at the potential influence of rainfall in volcanic environments, in particular where this may trigger or otherwise facilitate primary volcanic activity. Statistical analysis reconfirms previous observations at several volcanoes and suggests that they're symptomatic of a broader link between volcanism and the hydrological cycle. Moreover, we demonstrate that pressure transfer models yield pressure fluctuations at magma-relevant depths in line with previously theorized trigger stresses. So quasi-static stresses induced in this manner can bring around a long-lived increase of pore pressure above hydrostatic, in contrast to the short-lived dynamic pulses observed at shallow depths. We anticipate that satellite-derived precipitation data will prove invaluable in integrating rainfall into future quantitative studies and volcano monitoring programs. As ongoing climate change is projected to result in increasingly extreme rainfall patterns over the coming century, the potential for rainfall-triggered volcanic activity may be set to increase in the future. And critically, rainfall is both measurable and to a degree forecastable. So the inclusion of continuous ground and satellite-based meteorological monitoring in tandem with simple models of pressure transfer could prove invaluable in providing some advance warning of these hazards. So thanks for listening.